Hi, this is Dane Quinn from the University of Akron, and today's lecture will be on the moment of inertia. So, the moment of inertia essentially describes the mass distribution of an object B relative to some point A. So, as we see here in this figure, the moment of inertia characterizes essentially the shape of the object together with how the mass is distributed. And we denote that as I of B about A. So where does this come from? Well, recall from angular momentum balance, when we derive the equations of motion, and there is a previous lecture that concerns the derivation of momentum balance, both linear and angular momentum balance. But we saw a term that looked like the following. It was the integral over the body of r dm with respect to A cross the angular acceleration of the body cross, again, r dm with respect to A. And this was then integrated over the body. And at the time, we said this is defined as the moment of inertia about point A of the body times the angular acceleration of the body. So in general, for three-dimensional kinematics and three-dimensional motion, this moment of inertia is actually a matrix or a tensor. And so we're multiplying the matrix times the vector of angular accelerations. However, for planar objects, which is what we will consider in this class, again, motions or objects that move only in the plane, in this case the plane of the paper or the computer screen, and rotate about a spin axis that is normal to the plane. So for planar objects, this matrix simplifies to a single number, a scalar number. So let's look at that. And this we actually discussed briefly in the lecture on angular momentum balance. But we'll repeat it again. So here, r dm with respect to A represents the vector from A to some mass element. And again, when we ultimately integrate over the body, we'll integrate over all mass elements. But again, for planar objects, we can describe this vector in terms of directions fixed in the body. So let's say E1 and E2. Again, this is a frame of reference, set of basis directions that's fixed in the body. Then this vector can be described by the two coordinates S1 and S2, so that r of dm with respect to A is equal to S1 in the E1 direction and S2 in the E2 direction. Again, E1 and E2 are fixed in the object, so as the object moves around, then E1 and E2 move with it. And as a result, since A and dm are both fixed in the object, S1 and S2 are constant. So, in addition, as we had mentioned, the angular acceleration is only in the k direction. So we can write alpha b as some scalar value in the k direction. As a result, the argument of this interval, which is r of dm with respect to A cross alpha cross r dm with respect to A, reduces to s1 squared plus s2 squared times alpha in the k direction. And so you might want to pause this and take this expression, put it into r cross r, and verify that you get s1 squared plus s2 squared alpha k. But now, looking at this quantity, s1 squared plus s2 squared, actually is simply the square of the length of the vector r dm with respect to A. So we can actually write this as the magnitude squared times the angular acceleration of the body. So now, just a little bit of notation. Let's define this magnitude as simply s. So that this integral, the moment of inertia, r cross alpha cross r, simply reduces to this integrated over the body. Or, because the angular acceleration is constant as we vary the mass element, of course the angular acceleration doesn't depend on which mass element we choose, it's actually a property of the motion of the entire object, then that's constant when we integrate over the body, and we can factor that out, leaving the integral over b s squared dm times the angular acceleration. And it's this piece in brackets that is the moment of inertia of the body about point A, and then again times the angular acceleration. So we refer to this again as the moment of inertia for this planar object and this is actually said to be about the axis K, which comes out of the board, same direction as the angular acceleration, and through the point A. So again, this quantity is simply a function of the mass distribution of the body relative to point A. As we change A, then the value of s would change for each mass element, so we might have a different moment of inertia depending on the point that we choose. Certainly for different objects we'll have a different moment of inertia, but the important thing is that this is actually a property of the object. It's something that we could measure ahead of time without regard to the motion that this body is actually undergoing. So in that sense, it's a physical property. It's sort of like the mass of the object, right? The mass of the object doesn't depend on how the object is moving, and the moment of inertia is the same. So now, a little more about this. Because again, as we said, the moment of inertia about point A comes from this integral r dm with respect to A cross the angular acceleration cross r dm with respect to A. And as we mentioned, as we change the point A, we will change this moment of inertia. Well, it's not terribly convenient because that means every point on the object has a different moment of inertia, potentially. So I don't want to have to go and calculate the moment of inertia about every point. I'd like a simple way of expressing the moment of inertia that will allow me to determine the moment of inertia about point A, where A can be any point given some other known things. So the way that we do that actually is to identify the mass center G. So we have a vector r of G with respect to A. We now have a vector r of dm with respect to G, and as before, and as given in the definition of the moment of inertia, we have the position of dm with respect to A. So here we will express the position of some mass element with respect to A as the position of G with respect to A plus the position of the mass element with respect to g. So now I'm going to take this expression for the position of dm with respect to a, namely in terms of the mass center, and I will introduce it into this for the moment of inertia. And when we do that, we end up with four terms. We have one term that essentially comes from GA, so it's cross alpha cross r of GA. We get another term that looks like r of g with respect to a cross alpha cross r of dm with respect to g. Right, so that's this term and this part of the equation. We'll have another piece that looks like, well, again, this term now into this first expression, dm with respect to g cross alpha cross r of g with respect to a. And then finally, we get contributions from dm with respect to g in both of these terms. So it's the integral over the body, r dm with respect to g, cross alpha cross r dm with respect to g. So now we're going to make use of the fact that we'd actually use the mass center, because as you recall, the mass center was defined as the specific point for which the integral over the body of r dm with respect to g vanished. So g is the center of mass. Right? This is the definition of the mass center, and this is what it means to be the center of mass. So now, with that, we see that r, g with respect to a, and alpha are constant over the body. So, in particular, in this term, the second and in the third term, we can factor out r cross alpha, and this integral comes right into here with the position of the dm with respect to g. But again, that's 0. So this term goes away. Likewise, for the same reasons, this term goes away, because alpha and r of g with respect to a are constant over the body. As a result, the moment of inertia about point A times the angular acceleration reduces to just these first two terms, rga cross alpha cross rga and r dm with respect to g cross alpha cross r dm with respect to g. Well, we can actually simplify these as well, because this whole argument is constant. So now, for planar objects, sort of looking back at the same reasonings we gave when we reduced this expression to simply a scalar times alpha on the previous slide, we can show that this term becomes the total mass of the body times the magnitude of g with respect to a squared angular acceleration of the body. Likewise, this term is actually just the moment of inertia about the mass center times the angular acceleration. Compare this and this term. If I simply replace a with g up here, I get this integral. So again, this is the moment of inertia of the body about the mass center. As a result, we see that what we started off with, which is the moment of inertia about A, is equal to, well, both of these have alphas. I can factor that out. So I'll actually write this term first. IG B plus M times the distance between G and A squared times alpha. So now comparing these two, we see that the moment of inertia about A of the body is the moment of inertia about G of the body. And again, G is a special point. It's the mass center. It's not just any point that we like. It has to be the mass center in this case. Plus M times the distance squared. Again, D here is defined as the distance between the mass center and the point that we're interested in. So this is known as the parallel axis theorem. And it relates the moment of inertia of the body about point A, and A can be any point, to the moment of inertia of the body about G, and here G is the mass center, so it's a specific point, and the mass of the object together with the distance between A and G. So we can use this to describe the moment of inertia about any point on the object or off the object to the moment of inertia of the body about the mass center. So now what else? Well, composite objects. So imagine that we have an object that can be decomposed into two or more components. Right, so maybe these are simple objects like bars or blocks or discs, and we essentially weld or connect two of them or two or more of them together. Right? So the moment of inertia, so here's the original object, and again that's B. Let's assume that it's composed of B1 and B2, and I would like to find the moment of inertia of the body, the original body, about point A. Well, of course we know how to do that, thinking about this as a single object. So we have the position of dm with respect to A, and we will describe the moment of inertia as the integral over the body of s squared dm, according to the previous slide. Here, s is, again, the magnitude of dm with respect to A. So now let's look at the object and think about that as being composed of two parts. Right, so maybe here's where I separate the two. And again, they're really not distinct objects. They're combined. This is a composite object. But I want to treat this part separately from this part. So here, the integral of the body, well, I can just break that up into the integral over the first part of the body, B1, and the integral over the second part of the body, B2. But now this S is the distance between A and some mass element on the body. So here, if we have a vector dm1 with respect to A, then we can identify the length as simply S1. So that's the magnitude of the position of this mass element with respect to the body. And so with this viewpoint, the distance between A and this mass element is simply S1 squared dm1. I can do the same thing for body 2. So we'll define the vector from A to dm2 like so, and S2 is defined as this magnitude, then this second piece, simply the integral s2 squared dm. So we have the integral over the body 1, integral over body 2, and here we notice that this is simply the moment of inertia of body 1 about point A. And this second term is the moment of inertia of body 2 about point A. So again, for composite objects, we would look at the moment of inertia about point A of one part of the object and add that to the moment of inertia about point A of the second part of the object. Now notice that over in this picture for beta, or for body 2, A is actually a part of the object, while for body 1, A is not physically located on that part of the object. But that's fine. Doesn't matter at all. We can find the moment of inertia about really any point. It doesn't have to be fixed in the object. It doesn't have to be connected to the object. It can be a separate point, as we've shown here in body 1. But composite objects, the overall total moment of inertia about point A is simply the sum of the individual components. So that makes constructing complicated objects a little more straightforward in terms of finding the inertial properties. So the last little bit refers to the radius of gyration. And this is just a different way of defining the moment of inertia. So the radius of gyration is denoted as KAB, is defined in the following way. It's the square root of the ratio of the moment of inertia of the body about point A divided by the mass of the body. So if I know the moment of inertia and I know the mass, I can calculate the radius of gyration. Alternatively, of course, if I were to give you the mass and give you the radius of gyration, then you could calculate the moment of inertia, because IA is m times Ka of the body squared. So why would we want to do this? Well, some nice properties of the radius of gyration arise. This has units of length, so it can actually serve sort of as a characteristic length of the object. Now, in addition, for objects with uniform density, the radius of gyration is independent of the density. So really, it's independent of the material. It only depends on the shape. So how can we show this? Well, what is the density? If I know the mass, then the density of an object is defined as the mass divided by the volume. So as a result, my differential mass element, when I go back to the definition, for example, of the moment of inertia that we saw on previous slides, is the density times the differential volume element, and the density would be constant over the body. So then looking at this definition, we see that Ka of the body, and I'll look at the squared quantity so I don't have to worry about the square root, is the moment of inertia. Well, the moment of inertia was the integral over the body of s squared dm, but now dm is rho dv, while the mass is the integral over the body of simply rho dv. Well, since rho is constant, we can factor rho out of both of these integrals, and then they cancel one another out. So what we're left with is the integral over the body of s squared dv divided by the volume of the object itself. Again, this doesn't depend on the mass of the object. In particular, it doesn't depend on the density of the object, because we assumed that the density was uniform. It's only a function of the shape, but not the material. So what that means is that if I were to make an object and I wanted to know what happened as we changed material, the radius of gyration would stay constant. However, the moment of inertia would certainly vary because the mass changes. So if I were to make an object out of lead, I would expect the moment of inertia to be much larger than if I made it out of, say, balsa wood, simply because the mass is larger. However, if the shapes of those two objects were the same, then the radius of gyration would be identical. And of course, the influence of the mass would come about through this relationship between the moment of inertia of the body about point A and the radius of gyration of the object about point A. So that's our discussion on the moment of inertia. Again, it's a property of the object in question, but it does not depend on the motion of the object. So it's something that we can calculate ahead of time. For this class, we'll commonly use things like bars and plates and disks, point masses, where the moment of inertia is well defined. It's easy to just sort of look that up in a table somewhere. For more complicated objects, such as you might see in real applications, you might have to go and actually calculate the moment of inertia of the object. But you'd only have to do it once. Once you had that, then you could go and look at the dynamic behavior of that object under lots of different physical situations. So that's it for this lecture. Thank you very much, and I will see you next time.